Okay, so this is an update video on some of the optimizations and modifications that I've done to the GU5B generator and power supply that I use for the WheelWork of Nature, and most particularly for the golden ratio or the golden dragon, as it correctly is, discharge. I've covered this generator and this power supply in a great deal of detail on my website. There are several posts on tube supply and also in the WheelWork of Nature experiments. Now, I was recently in the United States working with Eric Dollard on our hybrid system. We've put together there the hybrid system for the flame speaker and the burning bush and some other fractal root and tree experiments there, and we were using a hybrid system where we're using the audio and high voltage racks that Aaron and Eric have been putting together, and I've also been assisting them with some of that. And we've been using my mini gen, or the universal VTTC generator, as a power oscillator in order to do a whole range of experiments, which we did video and they will be coming out shortly. I'll put them up on YouTube. They cover the burning bush experiment, also the Colorado Springs step 2, the update experiments, and we did quite a few optimizations and enhancements to the hybrid system. And what I've done is I've then added some of those optimizations back in the lab here on the WheelWork of Nature apparatus that we've got set up here. So I'm going to go through what some of those things are, and then also we'll do a run so we can see how much larger our discharge is. This is the golden ratio or golden dragon discharge. So just to run through what we've got here, on the right we've got, this was nominally 5 kVA power supply. It's now uprated to almost 7 kVA, and I will go through what the changes have been there. That's a very flexible power supply. As I said, it can be configured in many different ways. I've got a lot of write-up on that on the website, so I'll really just be going through the updates. That's on the right. Then in the middle here we've got the GU5B generator. This is being used as a power oscillator here. We can see the GU5B at the top here. This is the anode. There's the anode connection and the cooling chimney. And I'm going to be going into more detail in what changes are in there. And of course we've got the tube unit, the coil unit, which has got the big vacuum variable tuning capacitor underneath. And this is the original WheelWork of Nature coil. It's nominally a 3 megacycle coil, flexible tunable pickup feedback, and a number of other meters and connections that I'll go through in detail. So what I'm going to do is I'll move the camera in first of all closer to the power supply, the high voltage power supply, and we'll go through some of the changes that we've made there. So if we look in more detail at the high voltage supply, originally I had 3 transformers down here. Now these are 1.8 kVA industrial microwave oven transformers. They are RTRN A741s, 1.8 kVA each, and I had 3 of those, but only ever really used 2. So I removed the one at the end, and that's given me an opportunity to put a microwave oven inverter in there, which I use for other types of experiments. The output of that is much higher frequency, about 20 kilocycles, compared with the transformer, obviously, which is UK line at 50 cycles, and that's convenient for other experiments. So that just leaves the two transformers, and all of the CW experiments so far presented on the WheelWork of Nature are using those two transformers, and we have a level shifter. I'll just move the camera down here. So here is the level shifter with the diodes underneath here. That's a 4 microfarad level shifter, and open circuit, that will take the 6 kilovolts of the two series connected transformers up to, in principle, 12 kilovolts, but about 11 kilovolts you can measure. And fully loaded, that's going to come down, well, the transformers produce just over 2 kilovolts each. So the 4 and the 8 fully loaded, you could get to about 7 kilovolts. So that was then used for the WheelWork of Nature experiments. Now, one of the things that you find, because the GU5B is quite a powerful tube and the discharge that we're creating in that coil is very current rich, so you notice the thick white streamers of the discharge, then the overall plate current on the GU5B is quite high. So you can be running those tubes for short periods of time, anywhere between 1 and 2.5 amps plate current, which is high for the specification of the tube, but that tube is very robust. That's the Russian military GU5B, and it's more than capable of taking that for relatively short runs. So in the region of, say, about 5 to 10 minutes or so. Or at least that's my experience of these tubes anyway. I've never blown one of these tubes from this kind of experiments at those kinds of plate currents. And also there you're consuming in the region of about 100 to 150 milliamps grid current. So because of the high plate current, it tends to pull the voltage of the supply down. So what I did here was I added an additional 2 transformers. These 2 transformers here. So this is series. They're connected in series via this patch board here. This patch board is the way to be able to configure how all these are connected, and then you take the appropriate outputs on the back. So these 2 transformers are connected effectively parallel with each of their reciprocal transformers. So we've got transformer T1 is here, transformer T2 is here. Transformer T3 is in parallel with T1 and T4 is in parallel with T2, and these are connected in series via this patch board. So essentially we have 2 in series, 2 in parallel to make 4 1.8 kVA transformers. That's nominally 7 kVA worth of transformers. By the time you take into account the power factor, which is about 0.6 here, then you're looking at between 4.5 and 5 kilowatts of real power absorbed by this system, which is makes it a very powerful supply when you get to the 5 kilowatt level. The advantage of having those 2 transformers, extra transformers, is it helps keep the voltage up considerably. So before, with just 2 transformers, the plate voltage ended up being pulled down to about 4 kilovolts, even with the level shifter at plate currents of about 1 to 1.5 amps. So with the addition of these 2 transformers, then we can hold the voltage up to almost 6 kilovolts at maximum power. So at around something like 2 to 2.5 amps plate current, and that makes a significant difference to the discharge. So in other words, the length of and this is a CW system, so we're not doing any modulation, or not any cathode modulation or staccato. Obviously we're using level shifted, which is an amplitude modulated, effectively amplitude modulated signal that we're applying to the plate. So in a CW situation, as this is currently running, I will relatively soon I will do another video covering staccato controller with cathode modulation and different other types of modulation schemes and the effect that they have on the generator and the discharge and the considerations that you need to make. So it's CW system, so we can hold the voltage up to 6 kilovolts. Normally the GU5B is 5 kilovolts on the anode, fully loaded, but my experience is able to take considerably more than that. I've had the anode running up to peak voltages of around about 9 kilovolts for short periods of time, and I haven't gotten flashover. So it makes it a very good tube in that respect for this kind. I mean, it's a zero bias tube, so it's really intended to be run grounded grid, and that makes it very ready as an oscillator. In other words, it will oscillate very easily, and that's exactly what we want in a power oscillator. So this is set up as a Class C Armstrong oscillator, very standard type of power oscillator, and that grounded grid or zero bias tube is very suitable, especially at these kinds of power levels. I've noticed actually, in fact, it so readily wants to oscillate that we also need to take into account the parasitics and harmonics and all those kinds of things that go on, and in that respect it's important to protect the power supply and the generator against things like parasitic oscillation, and I'll come back to that in a bit. But I mean, we have the normal things in here. So for example, if I just move the camera, if we look at the meters at the front here, we see that we have the normal 100 nanofarad 104 50 volt bypass capacitors on all the meters, otherwise you end up soaking up RF in there. They don't read accurately, they go crazy all over the place, and then you end up burning them out. So that's completely removed with the bypass capacitors. Those are current meters, of course, so you only need to make sure that you've got a voltage rating on the capacitor which is more than what you would be expecting on the meter. So the 50 volt 100 nanofarad is absolutely suitable for a bypass capacitor. We've obviously got the RF bypass capacitor at the final output. This is a 16 kilovolt 472, so 470 picofarad doorknob capacitor, and that soaks up RF. When we're running at full power for about 15 minutes, that'll get a little bit warm. So it's soaking up RF that gets reflected back from the generator, and we don't want that running around inside of the power supply, affecting things like the silicon control rectifier that we've got here that we use to control power. It's one of the options that I use, produces a nice non-linear switching which also enhances certain types of experiments for the discharge. And then of course we've got all the low power stuff. So you've got things like these vacuum relays which are switched low voltage 24 volts, and it's important then to have bypass. So again, there's a, if you can see down there, let me zoom in maybe a little bit there where it's connected, you can just see at the back there is a bypass capacitor, again 104 100 nanofarad 50 volts, and those are around in various places where the low voltage would be. So for example, let's bring it back here, make sure that's focused. Down in the side here there we can also see bypass capacitors on the low voltage supplies at various places around, and that includes directly across the low voltage power supply itself, which is down in the back here. We can see the transformers from this side. So what I do here is I take an output, because the transformers can be switched into different phases from the front panel, switches down here. I've taken an output from the side for the two transformers. They come up through here, they can be turned on and off in the system, and then so if I turn them off like that, now they're out. I can just run on two transformers, turn on there. Now I'm running on 4 transformers. So that's how it's all set up on this side. I think that's all the main changes from the high voltage supply. A few other things are moved around. I repositioned the SCR so it's easy to take out if you need to make a repair for it. Otherwise, mainly the transformers to hold up the voltage, and now holds it up to 6 kilovolt instead of 4. So if we take a look at the generator now, so the generator part, here's the GU5. We've obviously got now a parasitic oscillation suppressor in the plate circuit. That's a 22 ohm, 20 watt ceramic resistor, wire wound resistor, covered by magnet wire. It's about, I think, about 1.5 millimeter magnet wire, wound about 13 turns over the top of that. That forms a very good block for high frequency oscillations, very high harmonics coming off the coil, causing parasitic oscillation on the plate of the tube, which can lead to various runaway conditions in the tube if that couples to the grid, and then you can end up with burning out a tube through parasitic oscillation. The other thing that you also notice with the, and it's a real telltale, is with this tube, zero bias tube that wants to oscillate very readily, you will find that if you're not careful, you get parasitic oscillations. It's going to start affecting the electronics around. So for example, inside of here I've got a low voltage 15 volt switch mode power supply that I use for some of the low voltage parts of this, particularly for example for driving the cooling fan. And I would find under certain types of conditions when I was running the coil, the fan would stop. And when I investigated that further, it was actually the power supply had stopped working, stopped supplying the 15 volts. It's not blown, but the parasitic high frequency, say UHF frequencies coming off of the tube, had interfered with the control electronics in the power supply, which caused the power supply to stop giving out a 15 volt output when the fan stopped. So the fan would suddenly go slow, stop, and then come back on again. So the way to deal with that is to put parasitic oscillation suppression in every place that you can. So obviously all the meters, power supply are bypassed, and I'm going to show you that as well. These meters in themselves, so the two, these are Western 425 RF ammeters, very reliable. They're thermocouple based meters, so you get very, very good reading, very good at high voltage. This is 5 amperes RF, this is 250 milliamperes RF for the grid current and the plate current. And I simply I got them perched here, made a mount to put them, and then they connect it. This is the incoming high voltage, HT. This basically is one side of the primary, and this is the grid current directly going to the grid of the tube. So we've got a feedback leakage bias circuit for the oscillator, and then after that it comes via this meter and then straight onto the grid of the tube. So this is the last step before the grid connection to the tube. So you can see the grid current and you can see the plate current here. I also have an additional meter, let me just swing down here. It's another Western 425 1 amp meter, although this is shunted because the currents can get high, so this up to is now 2 amps. And this obviously is that's the bottom end of the secondary coil to the plate. We are using a virtual ground here, so the bottom end of the secondary is connected to this metal plate. Nothing else is connected to this metal plate. The advantage of using this, and I went over this in detail in some of the experiments that we did in the United States with Eric Dollard, the reason for using this virtual ground is it forms a ground plane where the flux coming off of the coil during running is pulled down onto the ground plane rather than being radiated out into space, because otherwise a Tesla coil can act as a very good radio broadcaster of all kinds of different frequencies and cause a lot of interference, and we want to capture as much of that flux as possible down to the virtual ground. So everything here is mounted on an aluminium plate, and that reduces considerably, actually by almost about 90% of the radiated RF at a distance. And that also is good for the operator as well. So if you're obviously standing back, I run all of this system using a remote control for the power supply. You can stand back from it and it's not too aggressive. So that's the virtual ground. And there is a meter there. So I was just covering this meter here. That goes between the bottom end of the secondary and this virtual ground. And obviously it measures the current at the bottom end of the secondary coil. And that can be quite important in tuning and also in monitoring how the coil is behaving in terms of its quarter wave modes and the various modes going on, longitudinal and transverse modes going on as the coil is actually running. Again, you can use ordinary meters. I like to use Western 425 thermocouple meters. They are more difficult to get and more expensive. I tend to fuse them as well. These have got bypass capacitors, so you can see from this one here, if I just bring it down, there is put it up on its end, there is a fuse there. I like to put the fuse at twice the meter capacity. These meters are quite strong, but the fuse will blow and preserve the meter. I would rather that happen than lose the meter. So that's another consideration. So back to here, I'm going to take the top off and let's have a look inside. So I disconnect here the connection to the primary, to the plate, and lift this up. This simply removes, and then this is designed to slide out like so. And then if I bring the camera in, we can have a detailed look at what the changes are that we've made in here. So if I put it there, okay, so here is the cooling chimney. This is a piece of acrylic or perspex tube. It does surprisingly well with the heat. We can see around the top here it has taken some beating over all the experiments that I've done, but otherwise generally good. And I have the tube mounted vertically with the anode up. You can run these tubes. They're recommended anode down, but they run well anode up as well. And it's mounted here. And below that we've got the cooling fan. Now this size of tube requires quite a bit of cooling. So in the data sheet you're going to find it's around about 400 kilograms per hour, which is just over about 220 CFM or cubic foot a minute. And that's quite a high airflow. Normally you would get that from a kind of squirrel cage fan, but because of space here I'm using one of these computer fans or computer power supply fans, and you can get some this is a turbo fan here which runs up to just over 200 CFM. So it really sounds like a jet engine when it's running. So this is from GDS time. It's designed for computers. It's a normal 3-inch 92mm fan. You can buy it. I got it on Amazon, and it sits under here. Draws air in from the side. So I've got a side slot in there where it draws air in and up and blows it out the top. And because of the speed, the very high speed of this fan, when it's idling, I use now a PWM controller. So I put a little PCB here. Let me just show you. There we are. The little PCB there, which goes out to a potentiometer knob on the side, and I can adjust that all the way from turning off the fan, all the way from low speed up to high speed, and that's really good. And I'll show it in in action when we run. So in other words, when this is just idling, I have it at low speed, and when I actually want to run, then I'll turn it up to full. Now when it's idling, so the maximum specified for this tube in the data sheet's 150 degrees C, and that's largely because of the seals that go between the glass and the anode and the grid at the bottom. So the seals on this can only really take up to 150 degrees C. I have had it up to more than that. I've run these tubes, are very robust, and I've got some very hot in previous experiments, but obviously then you are down into how much lifetime you're going to get from the tube. So arranging the right cooling for this kind of tube is very important. So this fan can produce enough cooling for this to run at full power, full plate dissipation, which is 2.5 kilowatts. I mean, that's a hell of a plate input. I mean, if this was running grounded grid and you've got a 2.5 kilowatt plate dissipation and you're running it, say, at 75% efficiency, I mean, Eric Darlot can get it up to 90%. But if you're running, say, at 75% efficiency, that's a hell of an output power you can get off of this kind of tube. But of course, then you've got to deal with the cooling and the requirements. I mean, in a 24/7 always-on transmitter, then you would have a squirrel cage fan on the anode, and then you would have a tap off of that, a tube off of that, and you would provide about 20 to 25 CFM of cooling onto the grid and to the connections for the heater as well. They get roasting hot if they're not cooled. So the cooling works well. The fan I was using was much slower before, so this is a good upgrade now to the full cooling that this tube needs. So when this is running at lowest speed and it's just idling, it sits at about 60 degrees C at the anode temperature. When I'm running at full power, so say putting about 4 to 5 kilowatts of power, real power in, then this anode will go up to around about 120 degrees C at full fan speed. If it just sits at idle at full fan speed, then you drop right down to about 60 degrees C to 40 degrees C. And at full fan speed, 4 kilowatts of power sustained, then you're running at about 120, 130 degrees C anode temperature. So the cooling is good. Other things, also all the necessary bypass capacitors on the meters, and on the, we can see on the, this is the low voltage supply, so that's the input. It's got a mains bypass suitable for mains, incoming mains voltage or line voltage, and the normal 104 100 nanofarad bypass capacitor on the low voltage output, the 15 volt output. All of the meters here of course have bypass. There's also a large bypass on the heater circuit here as well. That's a 103 20 kilovolts, and there is a 222 or 2.2 nanofarads on the 10 kilovolts right at the heater inputs to the tube. So again, you've got those various optimizations as well, and that is enough to prevent parasitic oscillation on the plate. And with adding all of those things, I haven't seen that the low voltage power supply now has a problem under certain experimental conditions, but I haven't run it on all, especially the non-linear conditions with the SCR switching very abruptly. I haven't tested it in all conditions, but I've not had a problem with it before, like I did before. The other aspect is, I'll cover this more in another video, but I want to just spend a little moment here and mention it. I'll just take this round to the back of the system and show what's on the back. Okay, so here at the back, this is what I'm going to do a whole video covering staccato and modulation and all the different effects that it creates and stuff. Actually, probably several videos. But this is what I'm using at the back here on this system. It's a solid state relay. So this is cathode keying, essentially. So it's connected between the cathode of the tube and the generator ground, or the return line to the generator. And this is a SSR 40DA solid state relay. What's good about those, they're basically triac switches. They have opto isolation and zero detection crossing. So that helps considerably not to blow triacs in unusual situations, or if you get out of phase with it, or you get kickback from the tube as it stops oscillating and starts oscillating again, then you don't end up blowing with a zero crossing detection. It's opto isolated between the two. For this running, I'll just have it switched on, so it's just acting as a switch directly. And as I said, in subsequent videos I'll go into more detail about everything you can do with that. But I quite like these solid state relays. They are quite reliable, and you can switch them relatively quickly. They're opto isolated, zero detection crossing, to switch at the right point on the waveform so that it doesn't get too hot, or it doesn't go outside of the power temperature characteristics of the triac that it's got in it. They typically have a BTA 24800 in them, and they can be quite vulnerable if you're doing quite a lot of aggressive switching at high powers, but this seems to be very reliable. So just add that as another thing coming as well. Okay, so I think those are really all the updates that we've made to this system. What I'll do is bring the camera back round, and we'll just do I'll put the top back on, and let's zoom out a little bit. Okay, so let me just put the top back on this, bring the camera around. Do at some time need to upgrade these boxes. These are absolutely fine for prototype research, which is mainly what I do. I'll just connect the solid state relay in now. Okay, so I'm going to turn on. We can hear the fan come on. That's the low positioning. It's a reasonable airflow coming off that, but that's low. So if I now turn it up, I don't know how well that will come out on the video, but it's a lot, the airflow is now a lot higher and it's a lot more noisy. I'll turn it back down. So it's a very nice feature for the cooling. Okay, so I'm going to go and connect this up again, and then we're going to run it and see what kind of results that we get from these improvements. So I've connected everything up. The tube is now warmed up. It's just idling at the moment. I'm going to turn up the cooling to maximum, and first of all I'm just going to run it and show what readings we get on the meters. So I'm going to turn up the power supply, so we get discharge. You can see the plate current rising. Milliamps grid current, a very small amount of current in secondary. kilowatts, not very high. So I'm going to bring the camera back. Now 2 kilowatts of input power. Just let the copper cool down for a minute. 4 kilowatts of input power. So we'll just pause for a moment. We were running there up to 6 kilowatts. We had 2.5 amps plate current. We had about 150 milliamps grid current. And we got up to about 300 milliamps secondary current at the bottom end. And we see the discharge was quite large. The green that we see in the discharge is basically the copper starting to melt and vaporize. So we just bring it back a little bit, let everything cool down. Not too much heat. But our copper anode at the top of the coil is completely gone. Needs a tungsten tip really there. Would be good for running at these very high powers. So this shows the effect now of keeping the voltage up. We can get the voltage right up to, I was almost up to 7 kilovolts at the output of the supply, high voltage supply. And that's measuring RMS voltage. So the peak voltage will be right at the top end of the level shifter, right at the top of the cycle there. Cooling works very well. Okay, we'll have another run. 250 watts. Watts, 1 kilowatt, 2 kilowatts, 3 kilowatts, 4 kilowatts, very large discharge. Many gold dragons. So many golden dragons in the one, and that will grow even bigger with cathode modulation, or staccato control as it's sometimes called. So we'll just let the tube cool a little bit. Turn the lights back on. So that really, for the GU5B, is really a very nicely optimised setup now. So all the way from, zoom out, fully zoomed out, all the way from the high voltage supply through to the generator and the coil system. We've got the right meters, we've got all the right parasitic suppression, and as a result we can run flat out, making almost full use of the transformers. I will just check the transformer temperature. Transformers are only lukewarm, so it really is. Those 1.8 kVA microwave oven transformers really can push hard into this kind of system. We got up to almost 2.75 amps plate current, 150 milliamps grid current, and about 300 milliamps at the bottom end of the secondary. So we were pushing the system hard. Good. Okay, this concludes. Let's turn this just down. This concludes an update video on the GU5B generator, main generator system, and a high voltage power supply that I use for the WheelWork of Nature.